Okay, so let's take a flying quadrotor for example. So one of the great things about quadrotors is that it's relatively easy to make them fly, to make them balance themselves. It's something we can do in a neutral controls course here at MIT, okay? But it gets a lot harder if you want those to fly agilely through an obstacle field, if they have to navigate a forest, if they have to navigate a city, if they have to navigate even an office environment. Then suddenly there's a intimate connection between the control system and the perception system. And there's hard questions to be solved there. So right now you'll see, for instance, quadrotors moving slowly, building maps of the environment, using lots of power, and ultimately not getting as much done as they will be able to get in a few years. When our technology comes to fruition, we'll be able to dart through the office environments, building rich, dense maps if that's the goal, and accomplishing much more on the same amount of power. So there's a couple different approaches to getting stereo vision to work on a UAV right now. One of them is to carry more computational power. So there's a great group in Switzerland working on trying to put stereo vision into an FPGA. Okay, and I expect that that's going to be an extremely successful approach. Our approach has been different. We're trying to do less computation to get sufficient information about the environment. So in our group, we have an idea called push broom stereo, where we're basically doing a subset of the stereo algorithm computation. We're only checking for depths at about 5 meters. And because our plane in this case is flying so darn fast through the environment, we can actually build a rich map as we fly, even if we're only looking for detections at 5 meters. So our approach has been to use commodity cell phone processors on our chip, not special purpose hardware, but to show that with algorithmic advances we can make use of less data from the stereo vision algorithm to do all our navigation and control. It's interesting if you look at the sensor payloads on quadrotors and other UAVs. A lot of people today are carrying depth cameras or LiDAR technology. This makes the sensing problem relatively easier. Depth cameras have trouble in natural light. LiDAR, if you have a powerful enough LiDAR, can do well in natural light, but at relatively great energetic cost. I think many of us believe that the ultimate solution will be in computer vision, which is a nice passive sensor, which has no fundamental range limitations, but that requires sort of deeper algorithmic understanding than what we have right now. So it's interesting to see some of our work, for instance, is in trying to do real-time stereo vision on a UAV. We've got some of the first examples of that working now, and I'm excited about that as the future. But my guess is the short-term applications are going to see laser rangefinders used very effectively, and then when power budgets become a real issue, we're going to see a push for the more mature technology, for maturing the technology of stereo vision and the like, or new sensors we haven't invented yet, but probably passive sensors. One of the enabling technologies in our control and perception capabilities has been the use of optimization. So almost all of our algorithms are based on this notion of optimization, often a notion of convex optimization, a special type of mathematical problem where computers can solve it very efficiently. We've tried to make a story of finding convexity, finding the right way to write down hard problems like picking up an object with multiple contacts or walking dynamically over rough terrain in ways that it can exploit the best capabilities of our optimization solvers today. And the breakthroughs that you've seen have often been in the transcription of the hard dynamics problem into a problem that a computer knows how to solve very well through this optimization-based theory.